Hey everybody, and welcome to the Exam 1 review for Chem 90 for summer 2016. We have a list of problems that I posted on Blackboard and emailed out. We're going to work our way through these. Even if you can't make it to the event itself, you'll have the chance to go through this. I will post the video afterwards, just so you can have the extra practice and see a few extra worked examples. If you're participating, feel free to ask questions. I will see those and you'll be able to see me mark those as I address them one by one. So let's start. We're going to start with problem 1. We're going to try to stick to the problems on the list. Feel free to ask questions about what I'm doing here, because that's the point of having the review. Now, first 2 problems deal with conversions. Conversions are going to be a major topic on the exam. To start this first problem, we need to map where we're coming from and where we're going to. We're starting in days, and we can't go days straight to minutes. So we can go days to hours to minutes. So this is a double conversion. Both examples that we're about to do are examples of double conversions. We start out by writing 2.8 days. That's how you start any conversion. You write down what's given. And I want to take it over to minutes. Well, each set of parentheses that you include is one conversion factor that you're going to work with. So one conversion factor is going to take me from days all the way to days to hours. And the second conversion factor will take me from hours to minutes. And that's where I want to end up. So the idea behind conversions is to cancel out units you don't want, so when we're done, we can get to the units that we do want. So I'm going to come over here. Opposite sides cancel, top and bottom. So I'm going to put days in the bottom. I'm going to put hours in the top. And let's see, in every 1 day, there are 24 hours. Okay, days cancel. And now I can tackle my second conversion factor. I don't want to end in hours. I want to cancel hours. And I can relate hours to minutes. For every 1 hour, I've got 60 minutes. So we can use our calculators. We can multiply across the top. 2.8 times 24 times 60. And that gives us 4,032 minutes. Or in other words, 2.8 days equals 4,032 minutes. Now when you're done, make sure that this makes sense. If you're converting 2.8 days into minutes, there should be more minutes than there were days, because minutes are smaller. And that's what we got. So that seems pretty reasonable. You wouldn't want something to say that in 2.8 days there were 0.5 minutes. That would have said that we messed up our conversion factors a bit. But this looks good. Let's move on to the second example. Pause the video if you want to try this on your own, but keep in mind our first example was days and minutes and hours. I'll give you those odd conversion factors. When it comes to milligrams and kilograms and our metric units, you have a table in your notes that you need to memorize. Those will not be given on the exam. So pause the video and give this a shot. Okay, so let's work the example. 1,284 milligrams, so mgs. And we want to take this all the way to kilograms. Well, you have a chart in your notes that helps us take milligrams to the base unit, the gram, and then we can take grams over to kilograms. So we need a double conversion. We're going to take milligrams on the bottom, and I can relate milligrams to the gram. Milli, just like millennium, 1,000. There's 1,000 milligrams in 1 gram. Now I don't want to end in the gram. The problem wants me to end in kilograms. So then I'm going to put the gram on the bottom over here so it cancels, and kilograms on the top. And there are 1,000 grams for every 1 kilogram. So we end up with our units canceling out right, giving me kg, or kilograms, to end with. And I get 1284 divided by 1,000 and divided by 1,000 again, which gives me 0.001284 kilograms as my final answer. Now, just a quick note on metrics. The chart that you have in your notes looks a lot like this. There are 2 columns. And we've got, let's divide it up here. We've got 1, let's say, gram on the top here. And we'll say that next comes 100 centigrams, 1,000 milligrams, 1,000,000 micrograms. Micro looks like a little U with a front tail. And then on the right side, we've got 1 kilogram equals 1,000 grams. Okay, now a quick note. This whole table that I just wrote out deals with grams, but we could just as easily replace all these little g's with capital L's. If I replaced all the little g's with capital L's, then instead of grams, we'd be looking at liters. If I replaced all the little g's with m's, then we would be looking at meters. So it doesn't matter what unit you use. It could be the gram, the liter, or the meter. Either way, the relationships hold true. So make sure you tackle your notes and memorize your metric units for the exam, because those will not be given. Okay, so we have some new viewers, and just as a reminder, this is going to be posted as a video. So we're working our way through the problems one by one. We just covered conversion, and I've got about 12 problems to work with you, and I'm going to try to stick to the problem list. That'll make sure that we can cover more material. Okay, so the second most popular topic on the discussion boards that will show up on the exam is density. Density we could tackle from 2 directions. Problems 3 and 4 that we're going to go over. One deals with math and solving an equation. The second deals with just looking at the definition of density and deciding if something is going to float or not. So first off, let me get rid of this goofy image at the bottom so we have a little more space to work with. There we go. Okay. And again, feel free to ask questions based on the problems that we're going over if you need any clarification on anything. Okay, we're given 2.2 gram candy. So I'm going to underline some of the key information. That takes up a volume of 1.89 mils. To the correct number of significant figures, what is the mass of the candy? Okay, if this was a test problem, you would be given also D equals M over V. So we have that to work with. Now we just have to label what we have. Gram is a unit of mass. And in the density equation, mass is M. 1.89 milliliters is a volume. And in the density equation, that's our V. So we've got M, we've got V, we can solve for D. Now we just have to plug it in. So density is going to equal, we'll draw a little line here, we're going to put M in the top, and M was 2.2 grams. G for gram, just an abbreviation for the unit. And in the bottom, we're going to put 1.89 milliliters, or mils, mLs, and then it's just dividing it in the calculator. 2.2 divided by 1.89. Let's plug that in and see what we get. Okay, your calculator is going to spit out something borderline ridiculous. I got 1.16402.116402. And the unit on that, grams per mil. Okay, looks like we have an answer, but we really don't, because it says to the correct number of significant figures. You had two separate rules, one for addition and subtraction, and one for multiplication and division. Well, we're dividing here. And your rule for division was, let's write it out here, keep the fewest Sig Figs in any number multiplied or divided. So let's look at the two numbers that we multiplied and divided, 2.2 and 1.89. Well, these don't have any zeros in either number, and non-zero numbers, so non-zero equals always significant. So that makes our job a little easier. So we've got a significant 2 here and a 2 here. That's a total of 2 sig figs in the top. If you look at the bottom, the 1, the 8, and the 9 are all significant. So we've got 3 sig figs in the bottom. And we'll cover sig figs a little more in depth later in the review. But for now, if we're doing division and we have to keep the fewest, well, we're going to keep the 2. So I need to keep 2 sig figs in my final answer. So I'm going to keep this 1, and I'm going to keep this 1, but I need to cut it off here. And whenever you're doing rounding, you keep your 2 sig figs, but look at the first digit that you're going to cut off. Because this 6 is 5 or higher, that means I'm not going to write down 1.1 for my final answer. I'm going to round it up to 1.2 with units of grams per mil. That's my final answer for density. Okay, remember, if you have any questions while we're going through this, please let me know. What I'd strongly suggest is going back through these practice problems after the review, and then just treating this as a video key and just pause and start it as you need to, and you get some extra practice in. Okay, problem number 4, we're still on the concept of density, and it says, will the candy we just calculated the density for sink or float in water? Well, on an exam, you'd be given a little extra information. So given the density of water is 1 gram per mil. Okay, so we've got water. Pardon my artwork. We'll have a big pool of water. And in this pool, the density of all this water is 1 gram per mil. We take a piece of candy. We throw that candy into the pool. The density of this candy is 1.2 grams per mil. So the density of the candy is higher than the density of the water. And the rule is higher density materials sorry about that, my mic just cut out. Higher density materials are going to sink in lower density materials. So this candy, when we throw it in, because it has a higher density, is going to sink in the water and it's going to go straight to the bottom. But let's say we threw in styrofoam. Styrofoam is really light, it has a really low density, so a piece of styrofoam lower than the density of water would float at the top. So let's keep moving here. Next up. Okay, a new viewer or two. Keep in mind, we're working our way through all 11 or 12 problems. We're going to stick to the problems on the list, but feel free to type a question in if at any point during one of these problems you want me to pause to answer any questions on what I'm doing. Okay, problem number 5. How much heat is required to heat a 100-gram sample of water from 60 degrees to 80 degrees? Okay, a 100-gram sample of water is about, let's say, 2 shot glasses of water. So I want to heat a very small amount of water, about 20 degrees Celsius, so it's going to increase in temperature, so it's heating up. Our equation for this is Q equals ms delta T. Q is heat, and that's what we're trying to find. It says how much heat is required. M is mass. S is a value called specific heat, and it's just a constant. And delta T is change for the delta. That little triangle means change, and T is temperature. So we have to label everything so we can put it in. We've got Q that we're looking for, 100 grams. Well, that makes this a mass, and we're heating up from 60 to 80 degrees. Well, delta T is a change in temperature. So how much is our temperature changing? Well, if we ended at 80 degrees Celsius and we started at 60 degrees Celsius, that means my temperature changed by 20 degrees Celsius. That's how much it increased. So this 20 degrees is going to be my delta T, or change in temperature. So I can start popping things in here. I'm solving for Q. Mass is 100 grams. My specific heat is given, S. S is what we're going to plug in here. And it's the S for water because we're looking at heating up water. This is always going to be a value that's provided. And don't worry about the units here. They look terrible. We'll talk about them in just a minute. Worry more about the number because we're treating it just like any other number. 4.184 joules per gram degree Celsius. And then last in here, we put our delta T, change in temperature, 20 degrees Celsius. So calculators, we tap in 100 times 4.184 times 20, and let's see what we get. And I get 81, or excuse me, not 81, 83.68. And let's look at what the unit is. Grams on top, grams on bottom, they're going to cancel. Degrees Celsius on top, degrees Celsius underneath the slash here, they'll cancel. Leaves me with J's. Shortcut to this is, if it's mass, chances are grams. If it's temperature, chances are degrees Celsius. If it's Q, heat, it's going to be in joules. So I've got 83.68 joules when I'm done. Let's talk briefly about this specific heat. The unit was joules per gram degree Celsius. Joules was energy. So it's how much energy it takes to heat up a gram of a substance by 1 degree Celsius. So that's all a specific heat is. It's an amount of energy it takes to heat something up by a degree. Okay, moving on, and I know I have probably 3 or 4 examples on Blackboard for this. This is a pretty basic, pretty key example of a problem like you'd see on your exam. Okay, problem number 6. How many protons, neutrons, and electrons are in a single neutral atom of bromine? You will be given a periodic table. You'll see something like this on the table. And your table does have names next to each one of the element symbols. So if your problem asks you about protons, neutrons, and electrons for bromine, you don't have to know that Br is bromine, and I won't have you memorize the table. You can just look for its name. So we know bromine 79. If you ever see carbon 12, carbon 13, bromine 79, that little number that comes after it is the mass number, or mass number. I'm going to abbreviate it like this. And the mass number equals the protons, P, plus the neutrons, N. So the mass number gives us a sum of protons and neutrons. And a little hint here, the mass number is always going to be a whole number. Mass number is confused very often with this number down here. This number down here is not the mass number, it's the average atomic mass. Let's hop back up here for a minute. Bromine 79 is just one flavor of bromine. There's bromine 81. There are different isotopes of bromine, different mass numbers. If we take all the different types of bromine and we average their masses, that's where we get the average atomic mass. It's a weighted atomic average of all the different isotopes that gives us an idea of what your average bromine atom is going to weigh. So let's get back to the problem here. I know the sum of protons and neutrons. I also have a little information hidden up here. On the periodic table above the element symbol, we have protons. This is the atomic number. The atomic number helps identify an element. So we've already answered part of this problem. For protons, I've got 35. Now, my mass number is 79, and that represents my neutrons and my protons. If I subtract from that 35, which is the atomic number of bromine, I'm subtracting off the P. So if I subtract off the P, 79 minus 35, that's just going to leave me with the neutrons. So 79, being that it's 1023, I'm going to use my calculator. We get 44, and that's 44 neutrons. So the shortcut here is, and I'll write it over here, mass number, let me scoot this into the screen a bit, mass number minus atomic number equals number of neutrons. Now this is not an equation that I would give on the exam just because it's not really an equation. This is just a relationship that you need to know. Mass number, neutrons and protons, minus atomic number, just the protons, gives the number of the neutrons. Okay, so we got protons, we've got neutrons, last up is electrons. So electrons over here, we can figure out based on our number of protons. Think about this in terms of protons are positive and electrons are negative. And let's see, there's a key word in this program, or in the problem. How many protons, neutrons, and electrons are in a single neutral? Neutral or no charge. So if it's neutral, that means it's not positive overall, it's not negative overall, there's no charge overall. So that means there has to be a balance between protons and electrons. So if I have 35 protons, I'll have 35 electrons. Now, keep in mind, positive protons, negative electrons. If this had said are in a negatively charged bromine 79, pause the video. if it was a negatively charged atom of bromine 79, would I need more protons or more electrons? Because that would destroy the balance. All right, so if this was a negatively charged atom of bromine 79, I'd need more electrons. So I know I have a couple of you watching right now, so no worries. If you have a question, interrupt me at any point. I'm just making a quick condensed review for you guys for this hour, trying to power through some of this material. Okay, and questions can be asked lower right, so you can post questions at any time during the review. Okay. So here we go. Problem number 7. What makes an atom have a positive or negative charge? Well, we just introduced that idea roughly, but let's look at the structure of an atom. An atom has positive charge at the center, and then as you go away from the center, we've got negatively charged electrons. Now, something we didn't mention is in the center, we also have neutrons. Neutrons have no charge, protons have a positive charge, and electrons have a negative charge. So when it comes to looking at a whole atom and what makes it positive or negative, we have to look at relative number of protons versus electrons. Let's say I'm looking at an atom of carbon. Carbon has an atomic number of 6. We just said that 6 represents the atomic number. So that means carbon has 6 protons. So if I had a 0 charge atom of carbon, then I would have 6 electrons as well, because I'd have a balance. If I have equal numbers of protons and electrons, I'm neutral overall with 0 charge. If I had 6 protons and 7 electrons, it's no longer balanced. I've got 1 extra electron. Electrons are the ones that are negative, and since I have more electrons, it has a negative charge. So when we look at what makes an atom positive or negative, you look at relative numbers of protons and electrons. Now, just a quick note, if it's going to be carbon, notice all these examples have 6 protons. That's because the atomic number identifies the element. If it's going to be carbon, it's got to have 6 protons. So if I want a positively charged carbon atom, I'm going to have more protons. So I'll have 5 electrons. If we have 6 protons and 5 electrons, that means I have protons winning out. Protons are positive. That would make an atom of carbon with 6 protons and 5 electrons positive overall, where CHG is just abbreviation for charge because we're running out of space over here. Okay, so remember, ask questions if you have them. I'm more than happy to answer them. Otherwise, we're going to keep plugging through the review just so we can hit all our topics before we hit 11 o'clock. Okay. This was another popular question on the discussion boards. It's a question involving the relationship between food and energy. So food, we can think of in terms of 3 different classifications. We've got carbohydrates, we've got protein, we've got fat, and this turns into one big conversion problem because you're given 3 conversion factors: calories per gram of carbohydrates, calories per gram of protein, and calories per gram of fat. When we studied energy, calories equal energy. Just a way to express energy. So in each one of these conversion factors, we're looking at the energy contained in a food compared to a gram of that particular food. So the question is, how many calories of energy are contained in 1 tablespoon of Jif peanut butter? Okay, well, it doesn't really give us too much information about Jif peanut butter, so let's make up some. I'm going to pretend, well, you know what? We have Google, so give me 2 shakes. Let's look this. Jif nutrition information. We'll look up the creamy peanut butter because that's really the only kind of peanut butter. Let's see what we get. Okay, I've got 8 grams of fat. I've got 4 grams of protein. And I've got 3.5 grams of carbs. Okay, so in 1 tablespoon of Jif peanut butter, I've got fat, protein, and carbs, and we want to know how many calories of energy are contained in the 1 tablespoon of peanut butter. So let's start with the fat. So we've got 1, 2, 3 different conversion factors. I'm looking for the one that has fat in it. I want to get rid of the fat, so I'm going to put grams of fat in the bottom, and I'm going to put calories in the top. Because I'm trying to look for energy, calories describes that. My conversion factor says 9 calories per gram of fat. So 9 goes in the top with calories per 1 gram of fat. Grams of fat cancel. 8 times 9 is 72. And grams of fat canceled, so that left me with calories. We can do the same thing for protein. We just have to use protein's conversion factor. And I've got, let's see, 4 calories per gram of protein. So again, gram of protein, this time will go on the bottom, and calories will go on the top. 4 calories per 1 gram of protein. 4 times 4 divided by 1 gives me 16 calories. Just like setting up conversions, making sure we put things opposite sides, top and bottom that we want to cancel, leaving us with the unit that we want, 16 calories. So far, we have the calories from fat, and we have the calories from protein. Now it says how many calories of energy, and we assume total, are in that 1 tablespoon of Jif peanut butter. So let's go for carbs also, and then we'll look totals. For carbs, we've got 4 calories per gram, just like the protein. So 4 calories for every 1 gram of carbs. So grams of carbs cancels out. 3.5 times 4, that gives us 14 calories from carbs. Then if I want the total energy, I take all 3 classes, fat, protein, and carbs, and I add up their calories. 72 and 16 and 14, and grand total 102 calories. Final answer. Something to watch when you're taking the exam. This just said how many calories, assuming total. It may just say how many calories from fat, in which case we would have just done the fat calculation. Or it may have said how many calories from the carbs. Now we would have just done the carb calculation, and the answer would have been 14. So just be careful what the problem is asking for, and don't do more work than you have to. Okay. This is rough for students in 151, not just for students in 090. The idea of inexact versus exact properties and intensive versus extensive properties. So if you're having issues with this, you're not alone. Inexact versus exact, don't try to come up with new rules. You have 2 rules for this. Go with them and you're set. Exact is going to fall into one of a few categories. If something is counted, then that's exact. If something is a definition, then it's exact. Like there are 1,000 milligrams per gram, that's a definition. It's exact. We know it perfectly well, which is what exact means. How sure am I that I have 2 pens here? I'm pretty sure. 1, 2, it's counted. There's no wiggle room. It's exact. Okay, inexact is going to be anything measured. So let's start looking through these. My pencil is 5.9 inches long. How do we know this? Well, it's not a definition. All pencils aren't 5.9 inches long, so that had to have been measured. If it's measured, it's inexact. So I'm going to put an I for inexact. There are 12 eggs per carton. Well, 12 eggs per carton, we could say 12 eggs per dozen, and we could look at that one of 2 ways. 12 eggs per carton, we could say that's counted. 12 eggs in a dozen, that's a definition. Either way, this is an exact number. No wiggle room, we know it perfectly well. There are 12 pencils in the box. What do you think? Chew on this one for a minute. I just have a box, and that box has 12 pencils in it. Exact or inexact? Now, post your answer to this in the questions. Just write exact or inexact. You don't have to post a question. Just exact or inexact. What do you vote? Okay, and remember, if you agree with anybody's post, you don't have to post your own. There's a little button that says +1. You can say +1 to agree with them. That keeps it a little cleaner over on the questions tab. Okay, so Mary Lou has said exact, and I'll buy that. Okay, so there's one left in here that I wanted to go over that's not listed, and that's 2.54 centimeters per 1 inch. Now, I will tell you that there are 2.54 centimeters per 1 inch. That's a definition. It seems kind of weird to say that this decimal is exact, but it is. So even though it has kind of a funky longer number, it's not something clean like 12 per dozen, this is still an exact value because it's a definition. It's a conversion factor. Okay. So let's move on to number 10. So intensive versus extensive. We're going to break these 2 down before we try and tackle the problem. So intensive and extensive. The difference between these 2 is, for one of these 2 types of properties, the size of the sample matters. For the other type of property, the size of the sample doesn't matter. So we're going to break it down that way. For extensive property, size matters. For an intensive property, the size of the property doesn't matter. Or in other words, for an intensive property, it doesn't matter if we have a teeny tiny sample of something or a truckload, that property is still going to be the same. For an extensive property, The property is going to change if we have a small sample versus a huge sample. So let's start digging through these. The mass of chocolate is 2.2 grams. Okay, well, 2.2 grams happens to be the mass of a single M&M candy. Now, if I change the number of M&Ms I have or the amount of chocolate I have, the mass of that chocolate is going to change. In other words, size of the sample matters. So mass is extensive because if you change the size of the sample, you change the mass. The rope is 5.6 meters long. Well, I could have another rope that's 2 meters long. I could have another rope that's 200 meters long. Size of the sample matters. This is going to be extensive. The density of water is 1 gram per mil. Now this one's a little harder to swallow, but if I have a coffee cup that's full of water, the density of water that's in this coffee cup is 1 gram per mil. If I have a swimming pool and that whole swimming pool is full of water, the swimming pool has water that has a density of 1 gram per mil. Doesn't matter if it's a little sample, doesn't matter if it's a big sample, density is intensive. Okay, I want you to think about this last one. The temperature of the water is 98 degrees. So do your size check. Is temperature an intensive or an extensive property? So put a vote up in the question section and decide whether or not temperature is going to be intensive or extensive. So just a reminder, I just gave you guys a minute to think about this last problem. The temperature of water is 98 degrees Celsius. Is that intensive or extensive? Don't worry about being wrong. Okay, so I've got 2 votes for intensive, and I'm going to agree with you. Because if we go back to this example up here, it would be kind of ridiculous to have a swimming pool full of 98 degrees Celsius water, because that's 2 degrees short of boiling, but I could have it. I could have a coffee cup full of 98 degrees Celsius water. Say I'm making tea. So if we compare these two, it doesn't matter the size of the sample, I can still have 98 degrees Celsius water, so size didn't matter. So when you're deciding on intensive versus extensive, do your check. Think, does this property depend on the size of the sample? If it doesn't, it's intensive. If it does, it's extensive. So good job, Jay Hawkins and Mary Lou. So solid job on that one. Okay. Problem 11. Let's provide an example of each of these. So before we provide, well, we'll hit them one by one. We'll do the definitions as we go along. So heterogeneous versus homogeneous, these are both types of mixtures. And mixtures contain 2 or more substances. Heterogeneous just means non-uniform, or that it's not the same throughout. Homogeneous means uniform, or it is the same all the way throughout. So think about milk. Milk says homogenized. If you have a gallon of milk, and this is my terrible artwork here, you have a little cap on there. Okay, if you take a sip from the top of the milk bottle, it's going to taste the exact same as if you took a sip from the bottom of the milk bottle. It's uniform in color, it's uniform in composition, it's homogeneous. Now, if instead of milk, we look at yogurt, and in this yogurt cup, we peel off the top here, and you find out that this is fruit on the bottom yogurt. So we've got yogurt at the top And if it's strawberry yogurt, all the strawberries are on the bottom of the container. So if you have a taste from up here, it's just disgusting plain yogurt. Who eats that? If you have a taste from down here, it's like having a spoonful of strawberry jam. So it's different depending on where you are in the sample. It's non-uniform. If it's non-uniform, it's heterogeneous. Okay. Atoms, molecules, and compounds. Atoms are building blocks. If we flip over and look at the periodic table, it's a couple problems back. I've got all kinds of different elements here. I've got cobalt and nickel and zinc and gallium. All of the elements on the periodic table, think about Legos. There are blue Legos, yellow Legos. There are Legos that have just one little nub on top. There are Legos that have 8 of these on top. So they're different types and colors of Legos, but they're all building blocks. And each Lego is a discrete unit, a discrete building block. These are the most basic building blocks of matter, and each type is going to be different. Each type. Sorry about that, my wireless headset keeps cutting out. So, but they all have the same thing in common, and that's that they're the simplest building block of matter as we know it. So, moving down, molecules are going to be composed of 2 or more atoms that are bonded together. So, it doesn't say 2 or more atoms of different types, any other stipulations, just 2 or more different atoms. So if I have HCl, or if I have O2, or if I have CO2, this is an H. If we looked at our periodic table, this is hydrogen. If I look at a Cl is chlorine. And this is showing a hydrogen with a chlorine. Well, that's 2 building blocks, 2 atoms. So I've got a molecule. O with this 2 says I have 2 of these O's, and this is oxygen. Well, 2 atoms of oxygen gives me a molecule. I've got 3 atoms over here. I've got C, which on your periodic table, it's called a carbon, and 2 O's that are oxygens. That makes CO2, 3 atoms. That meets our requirement of 2 or more atoms, a molecule. Now, all 3 of these are molecules, but not all 3 of these are compounds. Compounds have to be 2 or more, or 2 plus atoms of 2 plus different elements. So let's look at these again. To be a compound, you have to be 2 or more atoms, still, just like a molecule, but it has to be 2 or more different elements. So our first example here had hydrogen and it had chlorine. If we look at the periodic table, hydrogen's over here and chlorine's over here. Each box on the table represents a different element. So I have 2 different elements that show up in HCl and 2 or more atoms. So that makes HCl not just a molecule, but it also makes it a compound. O2, on the other hand, just has oxygen. That's only 1 element. It doesn't meet a requirement down here for compounds. It doesn't have 2 or more different elements. So O2 is a molecule because it has 2 or more atoms, but it's not a compound because it doesn't meet the requirement for different elements. So look at CO2, and I want you to decide, is CO2 an atom, a molecule, or a compound, or maybe a combination? What have we got with CO2? So type it out in the question section. What do you think we have with CO2? Atom, molecule, compound? Going to give you just a minute to answer that one. You can tap in your votes. Okay, I'm getting compound. Let's see if we have any other votes coming in. Okay, so you're both correct that it is a compound. If you look at CO2, it has carbon and it has oxygen. It has more than one atom that shows up here. So it wouldn't be appropriate to call CO2 an atom, but it is a collection of atoms. And we'll learn later that this collection of atoms is bound together. They're all stuck together. And we can also say two or more atoms makes a molecule. So this is a molecule because it has two or more atoms. This is a compound because it has two or more elements. It has carbon and oxygen, meeting the requirement for being a compound. Okay. Next up, we get to Sig Figs. This is the last big topic before we get to the tour of the periodic table that's going to close this out. Problem 12, using proper Sig Figs, what's the result of multiplying 8.8 times 2? So if you just pop this into a calculator, your calculator will lie to you on the exam. It will not give you the correct answer if you're looking for Sig Figs. Not every problem on the exam is going to ask for Sig Figs. If it does, it'll say explicitly something along the lines of using proper Sig Figs. So if I take 8.8 times 2, I'm going to get 17.6. In a math class, this would be right. But in chemistry class, something's wrong. Now, we have to take that answer that your calculator spits out with a grain of salt. We covered earlier in the review, there was a rule for multiplication and division with sig figs. And the rule was we keep the fewest number of sig figs of any of the numbers that we were multiplying or dividing. So 8.8 has 2 sig figs, and 2 has 1 sig fig. So between these, you've got to keep the fewest. So 1 sig fig would be what you would keep. So this is kind of rough because what that says is it looks like I would just keep the 1. But right, J. Hawkins, I would keep 20 for my final answer. So what's often done is you'll round this to say 2, but then stop and look at your answer. 17.6 doesn't round to 2. 17.6 would round to 20. And that 0 at the end here is not significant, but it does play a role in making this a larger number and making the final answer 20. So 1 sig fig was kept in the final answer, 20 was our winner. Okay, so good job there, Jay Hawkins, on predicting the answer. Okay, we have covered the multiplication and division rule. Make sure you look back in the notes on looking at the addition and subtraction rule. It doesn't deal with sig figs and keeping the fewest sig figs. The addition subtraction rule deals in keeping the fewest decimal places. So be careful in the difference there if you're multiplying, dividing, or adding, subtracting. Okay, how many sig figs are in the following values? We'll do 2.60, we'll do 0.006, and we'll do 1.010. Okay, you had a couple of rules for significant figures, non-zero equals significant. I'm going to abbreviate here, signif. If you had a trapped zero, that was going to be significant. If you have a preceding zero, that's going to be non-significant. And the last rule was trailing zeros is going to be, let's say, significant only if decimal place present. And let me answer, let's see, Crystal Parker. Yes, Crystal, you do have to join Google+. You do have to create an account to be able to participate in the questions. Okay, so these are our rules. A quick note, preceding and trailing zeros has nothing to do where the decimal place is. So all three of these zeros right here are preceding. They don't precede the decimal place. They precede the first non-zero number, so 6. If I read to the right, all of these zeros come before that 6, that non-zero number. That's why they're preceding. And preceding zeros are non-significant. So if I have to count how many sig figs are present in my value, well, these zeros are not, but this 6 is. It makes for a total of 1 sig fig in 0.006. If we look at 2.60, I've got a 2. That's non-zero, and it's significant. The 6 is non-zero and significant, and the 0 is not trapped. If I had a 0 here between the 2 and the 6, it would be trapped. Instead, it's trailing. It's trailing, not the decimal place, remember. It's trailing the last non-zero digit. And the rule for trailing was it's significant only if there's a decimal place. Well, there is. It shows up in the number. So that makes that 0 significant. 3 total sig figs. Take a look at this last example and put your vote in the votes list on the number of sig figs that show up in that value. So 1.010, how many sig figs total? Let's see what we get. Okay, so I have a vote for 4 sig figs from Mary Lou, and I'm going to buy that. That looks solid. The ones that should jump out immediately are the ones. Good job, Jay Hawkins. The ones are non-zero. Non-zeros are significant. This first 0 is trapped. Trapped zeros are significant, and it's trapped between these two ones. This is a trailing 0 because it comes at the end of the value. Trailing zeros are significant only if there's a decimal place. We do have a decimal place, so check. We've got 4 total sig figs. So make sure you can count the sig figs, because counting sig figs is the only way we're going to be able to multiply or divide with sig figs. Okay, we've got 1 minute before the review is over, so let's wrap this up with a little bit of information on the exam and a quick tour of the table. Your exam has 26 questions. It's going to be 2 hours, and when you get to your testing center, you open up the exam, the questions will have the equations with them. All equations, all constants. You won't have to dig in a separate equations page or wonder what equation to use. It'll be with each problem. So, quick tour of the table and what you need to know. If you see the shaded step here, the shaded step is the metalloids. Everything in the upper right is nonmetals. Everything to the left is metals. So broad strokes, that's the periodic table. Each one of the squares represents a different element. You don't have to memorize them or their names, but I do want you to know their columns and how they behave. For example, it might be really good to know that this first column is the alkali metals, and they're incredibly reactive to the point where potassium comes into contact with water vapor from the air and it becomes explosive. So cesium will blow the bottom out of a bathtub. So you have very reactive metals that show up in the alkali metals. Second column in. Whoops. Okay, good. My mic's still working. Alkaline earth metals. Less reactive than the alkalis, but still reactive. Moving over, we've got group 18, the last column in the periodic table, being the noble gases, very non-reactive, very inert. Don't play well with others. Group 17 being the halogens. So in short, we have a video in your notes called Tour of the Periodic Table. Make sure you look through that. Make sure you're not just focusing on math problems in preparation for the exam. Do focus on the concepts as well, because not everything is going to be math related. Now, that does bring us to the very end of the review, and I do need to end on time. I have a suggestion here, though. I'm going to go over to Blackboard briefly so you guys can head over there with me. I'm going to share my screen. Let me pull it up first. Okay. Pulling up my Blackboard. Just so you can't see my password here. Okay. So you should be able to see my Blackboard screen now. I'm going to pull up your class. Okay, head up to the announcement, not the announcements page, the schedule and syllabus tab. And if you scroll down, you've got my office hours. It says see syllabus for details. So let's pull her up. So our syllabus, I'm going to share it with you. And give me just a second while it switches over. Should take just a second here. Well, it's being very disagreeable, actually. So let me write this down for you on the screen. And let me cancel this screen share so you guys can see what's going on. Okay, my office hours are going to be Tuesday, Wednesday, and Thursday. You can find me in my office on Tuesday and Thursday. I'm in TE 222. Wednesdays, I'm in LE 212. 3:15 to 4:15. That's the STEM Center. That's really great if you want to come in and get some help from me or just chemists in general. On Tuesdays and Thursdays, I'm in the office from 2:15 to 4:15. So please come into my office hours. If you have any additional questions, you can email me. My email is jrwhitehead@waketech.com. And lastly, take a look at Blackboard on the Remind app. If you sign up, you can text me questions, or you can get just general announcements about the class. But thank you for attending. It's awesome that you guys came out, especially this late at night. And good luck on the first exam. Let me know if you need anything from my end. So thank you for coming, and that's the close of the review. I'll supply the video later once it's done processing on YouTube.